Hi. I hope you had a nice lunch break, enjoyed the good food, and maybe also had some nice talks. What happens to me from time to time when I visit events like this and talk to people and they get aware of what I'm doing and where we're from, I get asked 3 questions. First of all, ProSiebenSat.1 and artificial intelligence, how come? The second, isn't linear TV dead? And the third one is, will Stefan Raab return to the screen? Some of you might know him. Well, we will not answer the third question today, but we will shed some light on the first 2 questions. This is Manuel, a data scientist in our team, who turns wishes, ideas, and requirements into AI solutions. He's with ProSiebenSat.1 now for 2.5 years and started as an intern. And today he is your expert and will present you the topic of performance marketing in linear TV. I'm Sebastian. I'm with ProSiebenSat.1 now for 5 years, always dealing with the topic of machine learning and leading the AI products department. Let's start to shed some light on the first 2 questions. So, yes, linear TV is losing market share in terms of or with regards to the consumption of motion picture content, but it's not dead at all. And the people at ProSiebenSat.1 were pretty early aware of the situation and developed a strategy to face the scenario. The first part of this strategy is that we digitize the consumption of motion picture content. By not just having a lot of different TV channels, we also have websites where we distribute our content, social media channels, as well as our own streaming platform, Join. But this is just half of the strategy. The other part of the strategy is that our company is based on 2 additional business models. One business model is dating and video, and the other business model is venture and commerce. And how this gets together, I will show you on the next slide. So, in the middle you see our main pillar, the entertainment pillar. It still stands for 50% of our revenue. But what was figured out at ProSiebenSat.1 pretty fast and pretty early is that we have to diversify our business model. So we invested the money that we earned in smaller companies, startups. And what we then did is we used the reach that we have, and this reach do we have still each day, so we're reaching millions and millions of people through our different channels. We gave those startups slots within our TV ads, and so made them known to a broader audience, to broader people, increases in sales of their products. And then either we create new pillars like the dating pillar, or we sell them if they don't fit anymore into our strategy. And you might know some of those companies. If we look at the e-commerce venture side, so the Urban Sports Clubs belongs to ProSiebenSat.1. Jochen Schweizer My Days belongs to ProSiebenSat.1. Verivox, Billiger Mietwagen, Amorelli. All companies that belong to ProSiebenSat.1, and if you watch linear TV, you will see their spots on our channels. On the dating side, that's the Parship Meet Group, one of the biggest matchmaking companies in the world. Parship, Elite Partner, Levu, eHarmony, all companies that belong to ProSiebenSat.1. What else is important to push those 3 pillars? It's obvious, it's technology. And this is where we come in, AI products. What you see here on this screen is our vision and mission statement developed within our team. And you might ask yourself right now, okay, what the heck, why tech departments or data science departments develop their own vision and mission? It's pretty simple. We don't see ourselves as just developers that turn requirements into a solution. We really want to shape ProSiebenSat.1 in the future and make ProSiebenSat.1 future ready with our skills, knowledge, creativity, and passion. The team I'm talking about is pretty diverse in different dimensions. So what you see here, these are all the roles within our team. And this puts us into the situation that we pretty much independently can develop AI solutions. But it's not just the skills and knowledge that is within our team, it's also how we manage to work together with over 20 people from 10 different nations. And this team is pretty successful. What you see on this slide is just a short selection of solutions, productive solutions that we developed. So I will detail 2 of them very quick. Automated tagging, what is this? So we're using machine learning algorithms to fully automate the process of content documentation and archiving. You all smart people, what we're doing is we create content and we want to reuse the content. So what we create for Galileo might also fit a little bit for TAF. And to support this reuse, you have to document and archive the content, and this is what we're doing with machine learning. Another example is targeting. So we developed a solution to tell our ad customers who's sitting in front of our different channels, either in the digital world or in the TV world. And a little bit more details you will get now from Manuel, who will talk about attribution modeling.
Thank you, Sebastian. So now we have some advertising customers that have some media budget and they want obviously to optimize this. And especially in the area of TV, that means kind of measuring performance of TV spots, using that data and then draw conclusions, for example, for future TV spots, for future campaigns on, for example, when should we add the ads to get most of the impact, like most website visits, on which channel, and question like this. This is a kind of complex problem, especially in the area of TV, which is not really perfectly connected to the online world. So we support those advertising customers basically in their advertising planning process. And you can see basically 3 pillars here. First, we have to identify who watched some spots in TV and reacted afterwards in some specific time frame on the advertiser's website. This is called attribution, finding out basically the impact of those TV spots that have been aired on TV. You can then analyze those results, and often advertising customers have some KPIs like cost per visit to kind of determine what the impact was, and cost per visit is obviously dividing the cost through the visits that have been induced by those TV spots. And then we can use that data after we have this to predict future spots, future TV campaigns, to optimize and then also optimize those predictions for the needs of our customers. Today I will mainly focus on the attribution part, that you kind of understand better how our data looks like and how we make it to that point that we then can use it for prediction models. And this is the second part. I will show you then how we build, or basically how we use this for our machine learning model to predict future website visits or future or those KPIs like the CPV I was just talking about. And last but not least, I will also share 3 learnings with you based on our journey on when we developed our machine learning model. So first of all, starting with attribution, I already said it's kind of difficult to combine the online with the offline world. And in the past, on the left-hand side, you can see the kind of classic approach where advertisers basically were tracking their website, and then they, after a spot was aired on TV, like 8 o'clock at Pro7, they track basically the visits before that spot was aired and afterwards. If there's a significant increase in website visits, then they would assign those visits to that spot that has been aired. And it's a bit more complex, like you have some kind of baseline you can compute based on some models, but this is basically the essence of it. We tried to build on that data some machine learning models, but were not that successful because there's a high noise in the data, so those website visits might come from different sources, and it was kind of hard for a model to learn something from that. Therefore, we came up with a new approach that it's more familiar to the online marketing audience, I would say, and we try to combine basically the offline with the online world. So we know basically then if a household has watched some TV spots, for example, from Flaconi, and then afterwards, if that household also visited the website of Flaconi. We can do this by the tracking pixel that you can see here, and the advertising customer basically have to implement this pixel on the advertiser's website, and then we can basically link via IP matching. We can then link the household on a household level, basically link both entities together, like the household that has seen the TV spot and also visited the website. So it's working not on a user level, so to speak, but on a household level, like basically on your router level, so to speak. This is the rough picture how it works. I will show you on the next slide basically how it actually works to do this attribution, because it might seem a bit intimidating, or it's not clear basically when you just look at that picture. And there are different attribution models that are used in online marketing, and we can basically use the same ones. We use a linear attribution model, and this is then how we basically can assign website visits to single TV spots. And here I brought you an example. Basically, you have three journeys of households and 3 website visits that those households have made. For example, the first household has seen spot 1, spot 2, spot 3, and then reacted. Household 2 has seen spot 1, spot 2, and then reacted. And household 3 has seen spot 2 and spot 3 and then reacted. Now, how can we split those website visits, or basically how can we assign those website visits to TV spots? In this linear approach, it's quite simple to just equally distribute for each household a website visit among spots. So the first spot, as you can see then here on the right-hand side, would get 1/3 from the first journey, because you just divide one website visit through the length of the chain, which are 3 spots. And it doesn't occur on the third household journey, therefore it gets 0, and for the second one it gets half of the visit. And this is also the result that you can see on the right, 5, 6. And when you sum those up for each spot, you would then again be at 3 website visits again, but this is kind of the process how we assign website visits to those TV spots. And this is then the core data that we use for our machine learning model to predict future website visits. It's not actually future website visits. We divide cost by website visits because we want to directly predict the KPI, but this is then the main data that we use for our machine learning model, which you can see on the next slide. So the red box here is the household tracking data. This is the cost per visit that is based on the visits that you have just seen, how we calculated it. And in the end, the output is the predicted cost per visit for, in our case, for the next 6 weeks. We train our model on just 5 weeks of data. I will later explain to you why that is the case. And we have some additional components that get into the model, like some metadata about the spots, like the length of a TV spot, what show is running before the TV spot, what show is running after the TV spot, what is the channel, what is the weekday, such features. Those get fed into our model to predict the CPV, and the model is a gradient boosted tree. So it turned out this is quite, among Keglers, it's a quite common algorithm for those typical regression tasks. And now those advertisers cannot directly use our raw data, or they have some specific needs, like they have some specific requirements, and we cannot just send them over our 6-week prediction. And therefore we built a tool, an API and a tool around that they can access, and they can put in their requirements, like, for example, I want to spend 30% of my budget on ProSieben. Of that, I want to spend 20% during 8 and 11 o'clock, something like this. So it's kind of turns into an optimization problem. I won't focus on our optimization engine, but we basically, after having done our prediction, we do some optimization on it, and then on the right-hand side you can see some example output of potential spots we would recommend them to book in the future on TV to minimize, in that case, their CPV, maximize visits with their specific budget. Now, along the journey on getting to our machine learning model, we had quite some experimentation and trial and error, and I want to show you now basically 3 learnings regarding to our machine learning model that maybe are also of use to you. The first one is starting with simple models. So 3 years ago, or even before I joined, we were quite enthusiastic about having some data, playing around with it, building some models. And obviously neural networks are quite high in relevance. And yeah, we just went ahead and started with the most complex model that were fun to play around with. But later it turned out it might have been better to start with simple models and maybe even stick to them. And what I mean is the following. This might get a bit complicated now, but I'll walk you through it. This is one of our evaluations we did, where we then found out that neural networks are basically not the right choice for our data and our problem. And what you can see here is 9 boxes with different time periods. And each of those 9 boxes has on the y-axis the error of the model, and on the x-axis different training days we trained the model on. And the color are different machine learning models. What you just have to focus on, I'm sorry, the tech department always wants to update my Mac. I'm just not getting here. Now I'm back. Okay. Yeah, what I was saying is the color comes from different machine learning models, and the red one is the neural network that was currently in production, basically, with the parameters at that point in time. And each of those very small bars, I don't know if you can see it, but it's not a complete thick one bar, it's just one small bar in each of those boxes. This is a test set of our production case, like 6 weeks, so a specific test set that we have used. And yeah, we did this basically over a big period of time to not get biased by having maybe just one test set and then basing our decision on just one evaluation that we did. That's why this is a rather big one. And what I want you to focus on is this one. You can see a very high error here as well for our model, and here as well. So the conclusion we draw here was you could have luck with our model and get good results, but you could also have bad luck, and in some test cases it was quite worse. As you can see the error, there is the most variability in the error of our neural network. That's one of the reasons we then thought, yeah, maybe we could tweak the model further, do some more experimentation But what you could also see is that some basic model also performed quite well already. So why investigating that much time into it and not just use a bit more a simple model that you can also investigate better? The second learning, you might have already guessed it by looking deeply into the first picture, is more data is not always much better. And I show you in a second what I mean by that. Usually in machine learning, you always train on the most data that you have, and the model in general performs better. And that's certainly true for deep neural networks. But in our case, the data is highly diverse, and it's not, old data is basically useless for us because we rely on the most recent data to make the best predictions. And here you can also see the output of some evaluations. Now it's a bit easier to understand because I averaged those bars that you have seen on the slide before. We did some other evaluation and I made it bit more readable. On the y-axis you can basically see the error of our model, and on the x-axis different training days. And yeah, you can then see from this picture that the error doesn't really drastically decrease if you use more data, like those 504 that you can see on that slide. There might be, as I said, different reasons. I think one of the core reasons is that we have a high drift of the target variable over time. And yeah, that's why we actually today train our model just on 35 training days. The last learning is one model per customer. Maybe you've seen it in the slide about the ML model. There I had it as a feature, the customer. But we found out that it makes more sense to use a separate model for our customer and not having just the customer as a feature and then train one kind of general model and hope that this model picks up the patterns. We did also some evaluation there. This is now not the evaluation, but in the evaluation it was kind of shown that by using one single model for each customer, we could decrease our error by about 15%, which is quite a lot. And here you can also see an example how the target variable differs for different customers. So on the y-axis you can see again the CPV, so cost divided through visit. And on the x-axis, 3 different customers for a specific month. The color of, so one dot is a spot, and the color of the spot is a different content basically. But you can see that customer 1 has aired, for example, a lot of spots in that month. You have a high range of CPVs, so you have very highs, but also very lows. For customer 2, it's completely different. You have less spots, you have rather low CPVs, and for customer 3, it's again different again. So this was the third learning. To sum it up, starting with simple models was the first one. Second one, maybe use also less training data. Much is not always better if it doesn't represent your inference data. And the third one is using one model for each customer. Here I have to mention one more thing. You might wonder how does it scale? So for 3 customers it might be fine, but what about 30 or 100? There you might have obviously issues, but for example you could then do some clustering, so cluster the customers based on the distribution of the target variable, have for example customers grouped in one group with a high CPV, middle or low or something like this, and this should also work then well for the problem. So I hope those learnings were useful for you and also in the process of developing your machine learning model. Thank you.